let mu be a Borel regular measure. On RD, and let F from RD to R be a mu measurable function. Let A, subset of RD, be a mu measurable set such that the measure of A is finite. Fix epsilon positive. Then there exists F epsilon, which is continuous on RD, such that if you compute the measure of the set where F is not F epsilon, and you intersect that with A, this set is a set of small measure. So I would like to use that to solve the following exercise, which is related to one of your homework problems. Assume I am given F from RD to R, mu measurable. I want to find F epsilon, which are continuous, such that the limit when epsilon goes to 0 of F epsilon of S equal to F of X for mu almost every X. So I mean that the set of X such that the limit of F epsilon is not F of X, this set will be a set of zero measure. So in my statement and the exercise, I am going to assume that mu of RD is not infinite. But it is enough to assume that mu is a random measure. Mu is finite on a compact set. So saying that it is not infinite, this is not a bigger restriction than saying that it is a probability measure. So I am going to impose these conditions which are not necessary for the result to be true. I am also going to impose that F is bounded. And then I am going to comment on the fact that this is not a restriction. So exercise. Let mu be a Borel regular measure on RD. And let F from RD to R be a mu measurable bounded function. So show that assume mu of RD is 1. show that there exists f epsilon, which are continuous functions on Rd, such that the limit when epsilon goes to 0, the integral over Rd of f epsilon minus f d mu equal to 0. So any idea what the proof? Okay, so let us take a risk to write a proof which we hope will work. We hope that by just applying directly that, let us hope that the proof will work, and we'll see how to improve the approach to get the proof right. So if I use the same f epsilon which is there, so let f epsilon be given by losing. I will have the integral over Rd of f epsilon minus f d mu is the integral on the set where f epsilon equal to f minus f epsilon d mu, plus the integral on the set where f epsilon is not f minus f epsilon d mu. So on the set where f equal to f epsilon, the integral is 0. And I want to show that this goes to 0. If that was bounded, f is bounded. If f epsilon was uniformly bounded, I will be done. Okay, so it is not uniformly. I don't know that it is not uniformly bounded, so I need to modify a little bit losing theorem. Okay. Any idea? Okay, so the assumption is f is bounded, which means f is smaller than a constant m. So take f epsilon given by losing. So assume that this is f. It is bounded. And assume that I take f epsilon. Assume that I take f epsilon like that, where the smallest value of f epsilon can become smaller and smaller. So what I am going to do, I am going to cut off f epsilon below by the value negative m and above by the value m. And the new function I will obtain will be closer to f if f epsilon was close to f. So to do that rigorously, the cutoff is obtained by the following. Let M be such that the absolute value of f is less than or equal to m. And I am going to introduce a cutoff function. Which is defined the following way. So this is the function phi of t, which will take the value t if the absolute value of t is less than m, the value m if t is greater than m, the value negative m if t is less than m. So observe that phi of t is less than t, and it is also less than m. Clearly, if t is less than m, phi of t is less than t. If t is greater than m, phi of t is m, and so it is less than t. If I replace f epsilon, if I want to cut off f epsilon, I am going to compose it with phi epsilon. So by losing theorem, there exists f epsilon continuous. Let me call it f bar epsilon. Such that the measure of a set where f is not f bar epsilon, this is less than epsilon. So I am using the fact that mu of rd is finite, so I can take a equal to rd in losing theorem. Set f epsilon to be phi of f bar epsilon. Now let us look what happened on the set where f equal to f epsilon. We have f epsilon bar is smaller than m. Because f is smaller than m, so if f equal to f epsilon somewhere, f bar epsilon is less than m, and so phi of f bar epsilon equal to f bar epsilon. Because when we are below m, phi of t is t. So I can conclude that on that set, f bar epsilon is f, which means that f epsilon is f. Now let me compute my integral. We have that the integral over rd of f minus f epsilon d mu equal to the integral on the set where f equal to f bar epsilon, f minus f epsilon d mu, plus the integral on the set where f is not f bar epsilon, f minus f epsilon d mu. But on the set where f equal to f bar epsilon, f and f epsilon are the same thing. So this first term disappears. And I am left with the second. By definition, f bar epsilon is smaller than m. F is smaller than m. Therefore, this is less than 2m, the measure on the set where f is not f bar epsilon. And this is smaller than 2m epsilon. So that proves the desired result. So we can make the following observation, remark. Note that in the above exercise, we have shown that in losing theorem, if f is less than m, one can choose f epsilon continuous such that f epsilon is also smaller than m. Indeed, if you choose the f epsilon of losing theorem and you compose with phi, you get a new function which is going to satisfy the property, because from this observation, the set where f is not f epsilon is a subset of the set where f is not f bar epsilon. And that set is of measure smaller than epsilon. Question? So let us solve another exercise. Let me call this one A. And the next one B. So here is what the exercise is about. If you have two measures, mu bar and mu, which are Borel regular, saying that mu equal to mu bar is equivalent to saying that mu of A is mu bar of A for every A. So if A is mu measurable, this is equivalent to the integral over Rd of the characteristic function of A, d mu, is the integral over Rd of the characteristic function of A, d mu bar, for every A. Now, I cannot say mu measurable or mu bar measurable, but let's say for every A Borel, because every Borel set is mu measurable and mu bar measurable. So the characteristic function are some particular function, and you see that they cannot be continuous. Now here is the question. Assume I look at another problem, the integral of phi d mu equal to the integral of phi d mu bar for every phi which is continuous and bounded. assume I know that. Does it mean I know this? Or conversely, assume I know this. Does it mean I know that? So in the homework problem, you have been asked to show that if this inequality holds for characteristic function, this is equivalent to say that it holds for all Borel functions, and that is equivalent to show that it holds for every continuous function. So the most difficult part of the proof is to show that if it holds for every continuous function, then it holds for every characteristic function. And that is what I want to comment on. So knowing such an identity will be very useful later because it is very convenient to work with a continuous function than working with arbitrary Borel function. So let mu bar be 2 Borel regular probability measure on RD. Show that if the integral over RD of phi d mu is the integral over RD of phi d mu bar for all phi which are in CRD bounded, then mu of A is mu of A bar, mu bar of A for all A in RD Borel. So any idea? For instance, can we use the previous exercise? So how? Okay, but which measure are we going to use? What will play the role of the measure mu? Okay, so for the first measure, we will find a sequence F1 epsilon. For the second measure, F2 epsilon. How do we reconcile? So how do we show that we can find? So this F epsilon depends on the measure mu. How do we show that if we have two measures, we can find an F epsilon which is independent? An F epsilon which is the same for mu and mu bar. So set nu to be 1/2 mu plus 1/2 mu bar. So if we find a sequence for nu, then it will be a good sequence for mu and mu bar. But I have a first issue to face. I need to show that it is easy to show that nu is a probability measure. Then you need to, it is easy to show that it is an outer measure. Second, I want to show that it is a probability measure. That is also easy. Then I want to show that is a Borel measure. That is a little bit more complicated. I want to show that it is Borel regular. That needs a little bit more thinking than. So if you put the difficulty, easiest thing, outer measure. Easier, probability measure. A little bit more difficult, Borel measure. And more difficult than Borel measure, Borel regular. So I am going to just show the Borel regular part. And if you see that proof, then you will know how to adapt. One, we have to show that first, nu is an outer measure. Second, nu is a probability measure. Third, nu is Borel. Nu is Borel regular. And as I said, these two are a little bit, completely easy, and this require a little bit of thinking, and I am going to keep my focus on that. So, call this 4i. To show 4i, we have to show that given A, a subset of Rd, there exists B, Borel, such that A is a subset of B, and nu of A is nu of B. So since mu bar are Borel regular, there exists B1, B2, Borel, such that A is a subset of B1, A is a subset of B2, mu of B1 is mu of A is mu of B1, mu bar of A is mu bar of B2. So how do I construct B? Exactly. Set B to be B1 intersection B2. Clearly, it is a Borel measure. And we have that this is true. We also have that is true. But B contains A. Therefore, this is true. Also, that is true. So mu of B is between mu of A and mu of A. Therefore, mu of B equal to mu of A. And the same thing in the second case. We have mu of A equal to mu of B, mu bar of A equal to mu bar of B. And so, mu of A is mu of B. Now, we can apply the previous exercise. Let A be in RD be a Borel set. So since it is a Borel set, the characteristic function of A is a Borel function. Therefore, it is mu measurable. It is also mu bar measurable. And so it is nu measurable. By exercise A, there exists F epsilon subset of C of RD such that the limit when epsilon goes to 0, the integral over RD of F epsilon minus the characteristic function of A d mu equal to 0. Now, we have mu of A is the integral over RD of the characteristic function of A d mu. So I can subtract F epsilon and add F epsilon. But since F epsilon is continuous, the integral of F epsilon d mu is the integral of F epsilon d mu bar. Okay. So I keep this, and now I can subtract the characteristic function of A d mu bar and add the integral of the characteristic function of A d mu bar. So if I rearrange, yes, mu of A minus mu bar of A this is the integral over RD of the characteristic function of A minus F epsilon d mu plus the characteristic function of A minus F epsilon d mu bar. And this is less than This is less than putting the absolute value inside. But that is exactly the integral over Rd of f epsilon minus the characteristic function of A d nu. And this goes to 0 as epsilon goes to 0. Therefore, mu of A equal to mu of A bar. Question? Say it again.
I think it's missing a factor or two there.
Yes. So it will be twice. Okay, so I am going to define the support of a measure when you are in a topological space, but I can restrict myself to RD definition. Let mu be a Borel measure on RD. The support of mu is support of mu, which consists of all x in Rd such that for all u in Rd open set containing S, mu of u is greater than 0. So this is the analogous definition you have for the support of a function. So let us see an example. So Q, the set of a rational number, let me describe it by Rn, n from 1 to infinity, and set, so let Q and set mu to be the sum n from 1 to infinity, 1 divided by 2 to the power n, delta Rn. We have mu of Q is equal to what? One. What about the mu of R? Is 1. Okay. So we see that mu concentrate on a set of very small measures compared to R. However, what is the support of mu? R. Okay. Indeed, if X is in R and U is open and S is in U, then Q is dense in R, therefore there exists Rn in U. And if I compute mu of U, this will be less than mu of Rn, but mu of Rn is 1 divided by 2 to the power n, and so everything is in the support of mu. So the set where mu is concentrated may be very different from the support of mu. So what we are going to do is we are going to show that first, the support of mu is a compact set, and second, it is the smallest closest set which has a full measure. So exercise. Let mu be a Borel measure on RD. First, show that the support of mu is closed. Further, assume that mu of RD is finite. Show that the support of mu is the smallest closed set in RD whose measure is mu of RD. Can I remove that condition and draw the same conclusion? So what will be an easy counterexample? Exactly. Take the Lebesgue measure and take a closed half line. The measure of half of the line is infinity, but it cannot be the support. Okay. So this additional condition is necessary, and we'll see that it is useful in the solution. First, we have to prove that O defined to be RD minus the support of mu is open. Right? Saying that the support of mu is closed is equivalent to the complement of the support of mu is open. So if you want to show that a set is open, you show that if you take any point in that set, there exists a ball which is an open ball which is centered at that point and entirely containing the set. Let X be O. By definition, S is not in the support of mu. Where exists. So choose U in RD. Open such that X is in U and the measure of U is 0. I want to show that U is contained in O. If I can do that, I am done. I will have shown that given any element of O, I can find an open neighborhood of that element which is entirely contained in O. So let Y be in U. I want to show that Y is in O. Why will it be in O? Okay. 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 So you are saying this is an open set containing Y, which is of 0 measure. Since mu of U is 0, we have that Y is in O. So we have proven that everything in U is a subset of O. Hence, O is open. Suppose mu of RD is finite. And let K in RD be a closed set. Such that mu of K is mu of RD. I want to show that the support of mu is contained in K, which is the support of mu is the smallest closed set in RD, which has the same measure with mu of RD. So here is the goal. Support of mu is a subset of K, which is equivalent to RD minus K is a subset of RD minus the support of mu. So I can prove either the first inclusion or the second inclusion, which are equivalent. Let X be in RD minus K. This is an open set. What can I say about that open set? what can I say about its measure? It's 0. Okay, and this is where I use that the measure is finite. We have mu of k plus mu of u is mu of rd. But mu of k is mu of rd. And I can do this simplification because mu of rd is finite. And so, hence, mu of u is 0. It means that I have found an open set u containing S such that mu of u is 0. And so X cannot be in the support of mu. Because being in the support of mu means that if I take any open set containing S, then mu of that open set must be positive. So we have proven that, in conclusion, we have proven that the support of RD of mu, K minus RD minus K, is a subset of RD minus the support of mu, which is the claim we were after. Okay, so I am done with the measure theory part. And I am going to start the review on convex analysis. So convex functions are some extremely useful function in the calculus of variation and in many fields. And they satisfy some amazing property. So we all know that differentiability implies continuity. F differentiable implies F continuous. And if we are in a compact set, this implies F is bounded. Right. And we have many counterexamples. With convex function, the following miracle happens. If you know that the function is bounded, it is continuous. If you know that it is continuous, then it is differentiable almost everywhere. And you can characterize the measure of the set where it is not differentiable. The set where it is not differentiable is a rectifiable set. D minus 1 rectifiable set, which is it is a countable union of manifold of dimension D minus 1. So this implication, F bounded imply F continuous. I can be on any arbitrary Banach space. I don't have to be in finite dimension. But for convex function, most of the things which happen in 1D happen in infinite dimension. Because convexity said something is happening along every straight line. So even if I am in infinite dimension, I am going to study what is happening along this straight line, and I can draw a lot of conclusions. So let us prove the continuity property and the Lipschitz property on the straight line, and then we will see that on the Banach space, it is a direct application of what happened on the straight line. So let me start with a brief review on convex analysis. So throughout the session, Y is a Banach space. So Banach space means norm space that is complete, in the sense that every Cauchy sequence is convergent. Y star is the topological dual of Y. So this is the set of linear continuous function. On Y. And let us consider the dual pairing. It is just a convenient notation. If Y is in Y and Z is in Y star, you use the notation YZ. Inner product is by definition Z of Y. So Z is a linear function. So Z is defined on the set capital Y. And so Z of small y makes sense. So definition. I am going to define what a convex set is. This second set, if I take S0 and S1 in it, I may be lucky the straight line connecting S0 to S1 will be entirely contained in it. I may be unlucky, the straight line will go outside the set. So this set is not convex. In the first case, no matter where I take my pointer x0 and s1, if I draw the straight line connecting s0 to s1, it is entirely contained in the set, and so the set is convex. So we say that X subset of Y is convex if for all t between 0 and 1 and all x0, s1 in X, 1 minus t x0 plus t s1 is in X. So if I let the t vary in R, I get the whole straight line passing through S0, S1. If I restrict t to be between 0 and 1, I get the segment starting at S0 and ending at S1. Only on convex set you can define convex function. Otherwise, the definition doesn't make sense outside convex set. Let phi from Y if S is convex, phi from X to R union plus infinity is convex if phi of 1 minus t x0 plus t s1 is less than 1 minus t phi of s0 plus t phi of s1 for all t between 0 and 1 and all s0 S1 in X. So you can see here that I want to ensure that if S0, if phi of S0 and phi of S1 are defined, then phi of 1 minus T S0 plus T S1 is well defined. And this is why I impose the condition that S is convex. The domain of the effective domain, but sometimes people don't say effective, of phi is dom of phi, which is a set of S in X, such that phi of X is less than plus infinity. So converse function which achieve, I am excluding the value negative infinity. It is never achieved. Converse function which achieve the value negative infinity are not very useful. For the following fact. So assume that my converse function achieves the value S infinity at X. Assume the value infinity at S infinity. Take any X arbitrarily. Now, write the straight line connecting S to S infinity and go over it a little bit. Why? So here I have S0. Set this to be S1. And that will be 1 minus T S0 plus T S1 for a certain T. Now apply this here. Okay. Let me exclude the case where f of y can be infinity. Then this one is negative infinity. That sum will be negative infinity. And so f of x will be negative infinity. So if I take a converse function, which is not plus infinity, if it achieves the value negative infinity somewhere, it is identically negative infinity everywhere. So this makes this class of function not very interesting. So you see, this is a condition on the behavior of my function along a straight line. So the graph of my function is like that. Okay. Or the graph is like this. It doesn't exclude that my function may have some discontinuity. So under this very simple assumption, we are going to check that phi is differentiable almost everywhere. And in fact, one can show that phi is twice differentiable almost everywhere in the sense that the Taylor expansion of order 2 hold. So let us see what happened on the straight line, because that is the more basic fact, exercise. Let phi from, let f from AB into R be a converse function. So to a pair of point S1, S2, I am going to associate the number, the slope, f of S2 minus f of S1 divided by S2 minus S1. Okay. So to a pair of points, I associate this real number. And what I want to prove is this slope is monotone, non-decreasing, if f is convex. So the precise statement is the following. Show that if A is less than S1, which is less than S2, which is less than S3, which is less than B, then f of S2 minus f of S1 divided by S2 minus S1 is smaller than f of S3 minus f of S2 divided by S3 minus S2. So I am claiming that the slope is monotone, non-decreasing. But to show that, you use an intermediary value. You compare the first value to f of S3 minus f of S1 divided by S3 minus S1. So I am going to show that this is smaller than that is smaller than that. And so the most left-hand side expression is less than the most right-hand side expression. I am going to express that S2 is between S1 and S3. So write S2 to be 1 minus t S1 plus t S3, where t is S3 minus S1, S2 minus S1. So let me check it. S2 minus S1 will be t S3 minus S1. So if this will be true, if I subtract S1 from S2, I'll get a t S2 minus S3. And so this is correct. Okay. So this is my statement. And you just plug a t in it, and you check that what I wrote is correct. So 1 minus t will be S3 minus S2 divided by S3 minus S1. And both of them are between 0 and 1, because S1 is strictly less than S2, and S3 is strictly bigger than S2. Since f is convex, f of S2 is less than 1 minus t f of S1 plus t f of S3. Okay, so let me write that differently. F S3 2 is less than 1 minus t f S1 plus t f S3. I am going to write the same thing in two different ways. I am going to subtract f of S1 from both sides. I'll have f of S2 minus f of S1 is smaller than t f of S3 minus f of S1. So I subtracted f S1 from both sides. But this, I can also write it 1 minus t f of S1 plus t minus 1 f of S3 plus f of S3. So I can write a t equal to t minus 1 plus 1. Which means that one minus t f of S1 minus f of S3 plus f of S3. So let me rewrite what is here. What is there is f of S3 minus f of S2 is bigger than or equal to f of S3 minus f of S1. Okay, so here this is a negative f of S3 minus f of S1, and I multiply that by 1 minus t. So when I move it to the left-hand side, I get what I wrote there, but it is what is missing is 1 minus t. So plug t by what it is here, you get the first inequality. Plug 1 minus t by what it is there, you get the second inequality. And that show that solve the exercise. Let us draw the following corollary. Suppose f from AB to R is continuous. Let epsilon be bigger than 0 and smaller than 1. So all I want is the interval A plus epsilon B minus epsilon is smaller, is contained in the interval AB. Then the restriction of f to the interval A plus epsilon B minus epsilon is Lipschitz. Okay. So the statement is assume that I have a convex function on a segment. Assume that it is taking only real value. It is Lipschitz, so stronger than continuous. So proof. Here is the picture. I have A, B, A plus epsilon, B minus epsilon. And I take X and Y in the interval A plus epsilon, B minus epsilon. This exercise tells me that if I compare f of y minus f of x divided by x minus y minus x to f of b minus f of b minus epsilon divided by epsilon, I have this inequality. So the slope is monotone, non-decreasing. Okay? So y and x being on the left and b minus epsilon being on the right, the slope of ys is smaller than the slope of b minus epsilon. Similarly, y minus x is on the right-hand side of a plus epsilon. Therefore, this is bigger than f of a plus epsilon minus f of a divided by epsilon. And so we are done. So this slope is contained between two numbers which depend only on epsilon, which means this ratio is bounded above and below. And that proves that we have a Lipschitz control. Now, let us go to infinite dimension, and we'll see that what is done here tells us immediately that even if you are in infinite dimension, then your converse function becomes locally Lipschitz. Meaning, if you restrict yourself to compact set, you have a Lipschitz function. Any question? So in the homework assignment, homework number 2, I have lay out step which will help you show the following. Assume I have a converse function on RD taking only finite value. Then the function is locally Lipschitz. So what I want to do here, I want to impose that in addition, my function is bounded. But that is not needed. It is just to get a quick result. But in the homework assignment, I have given the procedure you need to show. You need to use to show that if the function is converse taking only finite value, then it is bounded. And so since it is bounded, then it is locally Lipschitz. So here we are going to show that bounded imply locally Lipschitz. Exercise. Let f from x, let x subset of y be non-empty. So suppose x subset of y is a convex non-empty set. And the open ball of center S0 radius R is contained in S. Suppose F let me say the ball of radius 2R is contained in S. Suppose F is convex and bounded. Show that the restriction of F to the ball of center S0 radius R is Lipschitz. So you can see in this statement, I am defining a converse function which is bounded on a ball of radius 2 little r, say ball of radius capital R. Now I take a ball of radius capital R minus epsilon. Epsilon is very small. And I claim that on that ball, my function is Lipschitz. So in this statement, I take capital R equal to 2R, epsilon equal to R. But it is just not to introduce new letters. But you will can see that the proof will go through if I had such a more general geometric condition. So proof. Let x, y be in the ball of center R, S naught radius R. Yes? Yes. Yes, thank you. Okay. So I consider my ball of center S naught radius R, and I take S and Y in that ball. Now, draw the straight line passing through X and Y. It is going to intersect this ball at a point A bar R, and that ball at a point AR. It is going to intersect this ball at a point B bar R, and here at the point B bar. So to be consistent with the notation here, let me write a phi here. And let me write a phi there. Define f of t to be phi of 1 minus t x plus t y. I am not saying that t is necessarily between 0 and 1. T may be outside 0 and 1. So it is easy to check that f is convex. Since phi is convex, so is f. I can write that A R equal to a certain for a certain t by definition, being on this straight line, mean that AR can be written 1 minus t x plus ty. A bar R can be written 1 minus t bar R x plus tr bar y. And if I compute the distance between AR and A bar R, by definition, it is greater than or equal to R. Okay? Because if you take a point on this small ball, on this small boundary, and a point on that larger boundary, the distance between them will be bigger than or equal to r. Okay. But this is TR y minus x. Okay, so let me write r is less than or equal to AR minus A bar R, and this is TR y minus x. I do the same thing for BR. BR is 1 minus SR x plus SR y. B bar R is 1 minus S bar R x plus S bar R y. And R is less than or equal to BR minus B bar R. And this is equal to, that is T minus T bar R. This is equal to S R minus S R bar x minus y. Okay, so I just compute the difference B minus BR minus B bar R, and I compute the norm. And I see that this is what it gives me. Now, call this exercise A, and call that exercise B. By exercise A, f of 1 minus f of 0 divided by 1 minus 0 is less than f of TR minus f of T bar R divided by TR minus T bar R, which is bigger than f of S R minus f of SR divided by SR minus SR. Okay, so we have the inequality SR is smaller than S bar R, which is smaller than when T is 0, we have X. When T is 1, we have Y, which is smaller than TR bar, which is smaller than TR. Okay. Again, all these points are 1 minus TS plus TY for a specific T. Okay. And then I order the T. Here, I am expressing the fact that this point is between these two. So that gives me this inequality, and so on. So you have this inequality. But f of z1 is phi of x. F of 0, sorry, phi of y. Phi of x divided by 1. F of TR is phi of something. This something is smaller than the supremum of phi. F of TR bar is phi of something. Negative that is smaller than the infimum of phi. Now, from this computation, TR minus TR bar, you read from here that 1 over TR minus T bar R equal to x minus y is so R is smaller so let me write what is there is R is smaller than T. R minus T bar R, the norm of x minus y. So I have used the factor. I have used this fact that TR is bigger than TR bar to say that the absolute value of TR minus TR bar is TR minus TR bar. Now, I can rewrite this as 1 over TR minus T bar R is smaller than x minus y divided by R. So I plug that here. It tells me that I can bound 1 over T R minus T bar R by this. X minus y divided by R. Here you do the same reasoning. But I have my inequality. You will see that it will give you that this is bigger than negative sup phi minus f phi over R x minus y. And we are done. My Lipschitz constant is the sup of phi minus the f of phi divided by R. Any question? So again, this assumption which I impose is too strong. It is not needed. It is enough that my function take only finite value, and then one can show that it is bounded, and then as a consequence, one can do the following. So I will say 5 more minutes, and I will stop. This is like when you see the dentist. He gives you the impression that he's going to finish, and you gain some hope, and then he may take more time. So exercise. So I start by saying let phi be from X, which is a subset of R, to R union infinity, be a convex function. If you set phi bar of X is phi of X when S is in X, and infinity when S is not in S, you can check that the phi bar is also convex. So there is no loss of generality from now on, when I am considering a convex function, there is no loss of generality to assume that it is defined on the whole set Y. If it is not defined on the whole set Y, we can replace it by that extension. So let phi I from Y to R union plus infinity be convex function. For I, certain capital I. Set phi to be the sup over I of phi I. Show that phi is convex. So let t be between 0 and 1, and let x not s1 be in y. We want to show that phi of 1 minus ts plus ty is smaller than 1 minus t phi of x plus t phi of y. So we want to show that phi of 1 minus ex plus ty is less than this number. Okay, so how do we do that?
Just take the supreme 2 times.
Okay. So this is true. Right? By definition of phi I. But phi I being convex, this is true. So here it is S naught and S1. Now I can erase what is in the middle and write the supremum over I, and I am done. Hence, supremum over I in I, phi I of 1 minus t S naught plus t S1 is smaller than 1 minus t phi of S naught plus t phi of S1. Any question? Okay, so we can claim to each other that we have worked enough for today and stop here.